So let me say a few words, and then it's a pleasure on behalf of our Ghent Analysis and PD Center to welcome Professor Gerd Grubb to give a talk at our geometric analysis seminar. And Professor Grubb, of course, is a very famous and distinguished scientist in the field of analysis, micro-local analysis, pseudo-differential operators, and many other spectral theory, many other topics. And it is our pleasure and honor to have her lecture here. And so having said that, I will pass chairing duties to Joan Cardona to be in charge of Professor Grubb's talk.
Okay. Thank you very much. Thank you to all the participants. So let me just add, say some words about Professor Gerd Grubb. Professor Gerd Grubb is a Danish mathematician. Like Professor Ruchansky said, she's very well known for her research on pseudo-differential operators. Now, she is Professor Emerita in the Department of Mathematical Science at the University of Copenhagen. She got her PhD under the supervision of Ralph Phillips in the University of Stanford. Then she returned to the University of Copenhagen in 1966, where eventually she became a full professor in 1994. Just maybe of interest for someone, MassAINet shows 115 papers written by her with close to 2,000 citations. So as a giant in the fields of micro-local analysis and pseudo-differential operators, and maybe the more representative figure in these fields in recent times, it's our pleasure to have Professor Gerd Grubb in our Ghent geometric analysis seminar. So Professor Grubb, please start.
Okay, thank you for your nice words, and thank you for inviting me. It's a great pleasure to see people again. Many people see you again in this form. I like the Zoom form, it's so easy. So yeah, let me start the topic. First of all, the plan is that I will spend about half the time to tell things that you maybe know, those who have heard me before, have heard these things before, sort of to explain what the situation is, what the interest is. And then I will spend the other half to tell new results where the spectral parameter comes in, and also results with non-zero boundary values, and also here a spectral parameter comes in. And I've made a list of names that occur in the theory. I'm not going to refer to these names very carefully, but if you get a copy of the slides, here's some things that are good to know. Okay, so let me start the topic. Well, the basic example in this whole circle of ideas is the fractional Laplacian. Minus Laplace, to make it positive, lifted to the power a, and a strictly between 0 and 1. You can also take larger a, but that's not harder than this case. And it has become fashionable recently because it enters in finance, in probability and finance. It seems to be able to predict some financial products better than the ordinary Laplacian. But it also enters in mathematical physics and in differential geometry. And there are several ways to describe it. And the two most important ways are the following. One is to describe it as a pseudo-differential operator, very natural, with the symbol psi to the power 2a, psi absolute to the power 2a. And just to fix ideas, here's the Fourier transform with this convention. And the inverse is almost the same with a plus and another constant. And they serve to define an operator, big P with symbol little p x psi, by this formula. You take the Fourier transform of u, you multiply by p x psi, you Fourier transform back, consider this x as a parameter. You transform back to x, and then you get a function of x, and that's up p of u. That's this function of x. And in this case, the fractional Laplacian is the operator with psi absolute to the power 2a in this place. And then there's another way of viewing it, namely as a singular integral operator. And here is a formula. It's a kind of convolution. It is a convolution with the function 1 over absolute y to the power n plus 2a. So it's a very singular function, and you have to take a principal value to make sense of this, and then there's the constant in front. And actually, this constant times y to the power minus n minus 2a is nothing but the inverse Fourier transform of psi to the 2a. Still, the points of view on these two formulations are somewhat different. In the first description, well, that I use, there are natural generalizations to x-dependent pseudo-differential operators with symbols having an x inside, as I started out with. Let me say immediately what I require of the P here. It should be classical. Point 1, classical, it means that it is expanded in homogeneous terms of degrees. The order is 2a, so it's 2a minus j integer running from 0 to infinity. So the jth term is homogeneous of degree t to the 2a minus j in psi. Then it should be strongly elliptic. That means that the first term, the principal symbol, is positive, or at least the real part of it is positive, estimated from below by a positive constant times psi to the power 2a. And I want them to be smooth at 0, so I just require these things outside of a small ball. And for the third thing it should satisfy, it should be what is called even for short. It means that that symbols with an even j are even, and those with an odd j have a minus, they are odd. Okay, so these are the symbols we look at, and let me just give an example, because I've discussed it recently with some mathematical physicists. You can take the magnetic Schrödinger operator, is in here, and you can lift it, give it a minus and lift it to the power a. Then you have an x-dependent operator which is of interest and enters in quantum mechanics. The other point of view, I mean the integral formulation, is the one that's most used in probability and in nonlinear analysis. And it can be generalized to expressions with other kernel functions. Namely, you could take something homogeneous, again, but with another function k defined on the unit sphere. But you assume that this function is positive and even just in this simple sense. And then it's possible also to let k be less smooth than being C infinity, as I had it up here. And such integrals, the operators if defined are generators of Levy processes. And these operators are actually x-independent. I mean, here I think there's an advantage up here that there is a systematic theory allowing x-dependence. And the custom is to work with real functions and real kernels only. I mean, everything is real in many of the papers that are written from this point of view. Whereas, of course, functions have to be complex when you use the Fourier transform. So, and on the other hand, I must admit that the singular integral methods are more directly applied to low regularity situations, domains omega with low regularity. And the pseudo-differential methods demand a lot of differentiability, at least originally demanded everything to be C infinity in X. And so I felt a need to compensate for that. So I've done a recent work with Helmut Abels, who is very good at non-smooth symbols and even non-smooth domains. This was really the most important new thing. And we have worked out a version of the theory in a joint work just recently. Okay, I have to introduce some notation. My omega will be either the positive half space or a bounded open subset of Rn with some smoothness of the boundary, which will be specified when it's used. And then we use R plus to denote restriction from the full space to omega, and E plus applied to a function on omega denotes extension by 0. And these two little things, R plus and E plus, are often omitted and sort of understood, tacitly understood, but they should be put in when you need them for clarity. Okay, I need some Sobolev spaces, and actually LP Sobolev spaces. They're usually called Bessel potential spaces, and I just take them, I've called it the index Q, take them for Q from 1 to infinity, and here is the Xi in brackets, which is a smoothed out version of absolute Xi, which is useful here. So HSQ of the full space consists of those distributions that have the property then when you Fourier transform and multiply by Xi in brackets to the power S and take the inverse Fourier transform, this should lie in LQ. And if for Q equals 2, it's just the usual Sobolev space. And Q is usually omitted when it's equal to 2. And then I need two scales of spaces adapted to the set omega. Namely, one of them is HSQ, where I put a bar on it. That's the restricted space, the restrictions to omega of the distributions in the space over Rn. And the other is the supported space, namely the space where you take the distributions in HSQRn and single those out that are supported in the closure of omega. And let's call it, in my terminology, it's called H dot SQ. So I have a line here and a dot here. And that's something I learned from the book of Amanda. He likes the dot and overline notation. And it's actually, I find it very convenient when you are playing with both types of spaces. If they appear in the same formula, it's nice to put a line on one of them and a dot on the other. The dotted space is also called H tilde, or H naught in Lyon's Magenis, H tilde in more recent books, in Triple's books, and sometimes a ring over the H, but I use the dot. And as I said, when Q is equals 2, it's the usual Sobolev spaces, and we leave out the index. And I will remind you of one interesting fact, namely that HSQ with a line and H minus S Q prime with a dot, and Q prime is the dual parameter, the dual Lebesgue space. I mean, the LQ and LQ prime are dual spaces. These two spaces are also dual with respect to an extension of the L2 scalar product, the integral of omega of U times conjugate V. Okay, so now let me define the Dirichlet problem associated with the operator. So we take P equal to either the fractional Laplacian or one of the pseudo-differential generalizations that I mentioned. And then we define the homogeneous Dirichlet problem on omega to be this problem. And why is it necessary? Well, what does this mean here? Well, the problem with pseudo-differential operators is that they're not local. It's not obvious what you mean by apply them to functions on omega. So we take functions on omega that are 0 outside omega, or 0 on the open set outside omega. So this condition is natural when we want to apply P. So now we apply P to such functions, and then we restrict them to omega with R plus, and we want this to match F. So the problem is, given a function F on omega, find U, distribution U, which is 0 in the exterior, and such that PU hits F when you restrict to omega. So that's it's called the homogeneous Dirichlet problem. Sometimes it's called the homogeneous restricted Dirichlet problem because there's a restriction involved. There are some other versions that have other names. But okay, this is the one I'm interested in. And the nice thing is that it's not hard to solve. I mean, there are solutions. And that's by a variational theory that gives a good type of solvability in some Sobolev spaces. P is of order 2a, so it maps HS to HS minus a, minus 2a. And in particular, it maps HA to H minus a. And when we take the functions supported in closure of omega, I mean, this condition that I mentioned, then it's the dotted space I use here. I apply P to this dotted space, and then after application, I get into H minus a, and then I restrict to H minus a omega. So it's well defined as a mapping there. Okay, now let me just take the bounded case. Something can be, one can do similar things also in unbounded case. But now, from now on, I assume omega is bounded here. I look at the sesquilinear form defined on C naught infinity, the C infinity functions that are completely supported in omega. SUV, it's just PU times V conjugate integrated over omega. And defined on this space, it extends by continuity to a sesquilinear form on H dot A. And it satisfies this inequality, the Gording inequality, or it's also called a coerciveness inequality, namely real part of SUU is, thanks to the strong ellipticity, it's greater or equal to a positive constant times the H dot A norm squared, and perhaps corrected by subtracting a multiple of the L2 norm. Such an inequality holds. And then we can apply the Lax-Milgram lemma that I hope you all know, and we obtain an operator we call the Dirichlet realization, PD, and its domain consists of those functions in the domain of the sesquilinear form such that they hit L2, such that R plus of PU is in L2. And this operator, when you add the beta, is bijective from the domain onto L2. And for the fractional Laplacian, beta is 0. So it is simply bijective. I mean, simply PD itself is bijective from the domain onto L2. So given any function in L2, you can find a solution to the Dirichlet problem. And now comes, well, a little more to be said. Since omega is bounded, there's a compact embedding of H dot A into L2, and therefore PD has a discrete spectrum, and it's called sigma. And it's contained in a sectorial region opening to the right, sort of an angle opening to the right in the complex plane. Okay, and now comes the next question, that is, what is this domain really? And how do we find, also, how do we find the regularity of U if F is in a better space? In the domain, F is in L2, but we could also take F in HS for positive S and ask what is the regularity of U. Excuse me. And now I will give a quick overview of the results that are known here, or just some highlights of the results that are known. It has been known for many years, since Vishik and Eshkin. It's written up in Eshkin's book from 71, that the domain of PD, when A is less than a half, it's simply the space H dot 2A, the supported functions of order 2A. And that's the best possible because PD is of order 2A, so we can lift L2 up to 2A. That's when A is less than a half. If A is greater than or equal to a half, we have a more vague, or they had a more vague information. It's here. Says that the domain is contained in the dotted space with A plus a half minus epsilon. And epsilon always means any small positive number. So that has been known for many years. But then there were some recent results that came in when the problem gained interest in recent years. Also, Tong and Sarah wrote a paper that's very much quoted in and published in 2014, where they showed that when f is bounded, better than a 2, namely bounded, then u is of the form of d to the a times a Hölder continuous function for a small t. D is the distance to the boundary. So d to the a, that's the distance to the power a, where a is the order that I've been talking about all the time. And ct, well, in the later paper, they showed that t can go up all the way up to a. And they only needed omega, the set, to be C11 in their result. And after seeing at the time their result came out, I began to work on the problem too, and published results in 15 in the case of the infinity domain. And the two most important results there is when f is in HSQ with a positive s, then u is in this space. It's called the A transmission space. And this is sort of a strange space. I'm going to talk much more about it. But the interest is that it goes if and only if. I mean, if u is here, then f is there. But when f is there, u is just in h dot a, but solves the equation, then u must be in here. So it's the exact domain that is being determined here. And when you let s go to infinity, you find this result. When f is c infinity, then u is in d to the a times c infinity up to the boundary. Okay, and this space is called the A transmission space, stems from the A transmission condition introduced by Hermander, and that was absorbed in the condition I had about the operator having an even symbol that satisfies the A transmission condition. And the quick information about this space is that HA of S plus 2A is contained in the dotted space of order S plus 2A plus something more. It contains this piece also, but there's something more. There's a piece where you have the distance to the boundary to the power A, and then a space where you have a smaller order. You have your only order S plus A, not S plus 2A, but S plus A. You take the restricted space and extend it by 0. That's sort of a rough thing to do. You get some singularity at the boundary when you do that. Or you have a jump at the boundary when you do that, and that in some sense produces this power d to the a. And yeah, I should tell the story that the theory was initiated in a lecture note of Hermander that he wrote already in 66 and gave to a few people. Well, they gave it to the people who attended the lectures in Princeton, and he gave it to a few other people. I got it from him in 1980, and I didn't pay attention to it, and some other people also got it, but nobody has really taken it up until, I mean, when I began these things in 2013, actually. I found the notes and I said, oh, my goodness, there's something interesting there. And I read the notes, and they're very sketchy, and some proofs are incomplete, but I decided to try to make a publication. What happened? Oh, something happened. Can you see my screen now?
Yes, we can see your screen. Maybe.
Oh, you can see it. Oh, okay. So it's just that it became small. I'll try to make it large.
Maybe.
Again. Yeah, good. Okay, yeah, sorry. So then I should also say that those results I just quoted was the infinity results, and therefore and since the probability and nonlinear people like non-smooth domains, we made an effort to extend the theory to less smooth domains, and that was this joint work with Abels that I mentioned before, where we managed to extend that statement to C1 plus tau domains, where tau is greater than 2a, and S is up to tau minus 2a. And also about the same time, Abatangelo and Rosoton began to work with greater values on tau than the first result, which was with low smoothness, and they got more higher smoothness results also. Okay, now what is the definition of the A transmission spaces? It is the following. In the half space case, the transmission space with A of t is psi plus to the minus A applied to the space extension by 0 of h t minus A. And this operator chi plus to minus A is the order reducing operator with this symbol. So it lifts the space HS up to the space HS plus A. But with this special structure, it preserves support in Rn plus closure. So it preserves support in the right-hand side. It means it preserves the dotted spaces, but it works in a more strange way on the spaces with a line. But I can say something more specific. Well, first, on a general bounded C1 plus tau domain, the space will then consist of functions that are locally in an interior in HT, and at the boundary they behave like the space I defined here in local coordinates. And then I can only let t go up. Okay, now let's go to the Dirichlet realization and now take it in LQ also. I defined it already in L2. That's the operator PDQ, consisting of the functions in the dotted space HAQ such that R plus or PQ lands in LQ. That's sort of the basic Dirichlet realization in LQ, low order in LQ. And that will now, thanks to the regularity theorem I had on the previous slide, it will satisfy the domain is in the transmission space HQ A of 2A. So that's the case S equals 0 on my previous slide. And here I can say precisely what it is, at least when A is not equal to 1 over Q, namely, it is H dot 2A when A is less than 1 over Q, then we end up in a dotted space up here. And when A is greater than 1 over Q, it is the dotted space plus, as a direct sum term, d to the A times something that comes from a boundary. So the correct boundary spaces are Bezow spaces in LQ, in the LQ setting. So we have a Bezow space here, and we lift it by a Poisson operator, getting a space over omega, and then it has the factor d to the A. Okay, and the important thing to note is that all the spaces have a factor d to the A. Those that also Tom and Sarah showed, and also the ones we have. Here is it explicitly, and in this space, there's a factor d to the 2A. It's contained in d to the 2A times LQ. So all spaces have a factor d to the A. Okay, that was the introduction. And I see how I'm doing for time. I think I'm fine. Now I will go to more new results. So I will simply get into what can be said from the point of view of spectral theory. So first, most of all, I look at the operator p minus lambda with a lambda in the complex plane, not 0. And then one should think that it's possible to do everything just like I did for p minus lambda. But the problem is that lambda does not fit into the pseudo-differential calculus. Lambda is just multiplication by a constant, but it doesn't satisfy the hypothesis I had for p. Namely, you recall P was an operator of order 2A, and it had an expansion in homogeneous terms. So they're homogeneous of order 2A minus J. And then they had this parity requirement. But if A is different from a half, then all terms are of non-integer order. Then 2A is different from 1. And when you subtract J, you still get something that's not an integer. This is non-integer, so all terms are non-integer order. So order 0 doesn't fit in. And if A equals a half, then A should be, or the lambda should be like the 0 order term. But the 0 order term, that's P1, and that is odd. It has a minus. And lambda doesn't have a minus. It's not odd, it's even. So lambda doesn't fit in, so one has to do a little bit of work. So now we look at the eigenvalue problem. P minus lambda equal to, we'll look for functions u lambda, non-trivial functions u lambda, that solve P minus lambda u lambda is 0 in omega, and still they should be supported in omega. And what one does is one moves lambda u lambda to the right-hand side, then it is a priori a function in LP, in LQ, sorry. And then we use the regularity theorem to show something better about u lambda, and then we work on this and jack up the regularity, and the result we get is the following here. When the symbol is infinity and omega is infinity, then we get this result for the eigenfunctions. The eigenfunctions are in d to the a times C2a, Hilbert space C2a of omega up to the boundary, if a is different from a half. And it is in dA times the Hilbert space 2a minus epsilon if a equals a half. When a is a half, then 2a is 1, and we don't hit C1, but we hit C1 minus epsilon, or we get into C1 minus epsilon. And is that really best possible, one can ask? But yes, it is, in the sense that they are never in, I mean, when lambda is different from 0, they're never in a space dA c to the 2a plus delta for any delta greater than 0. So this is a kind of best possible result. And that was the first result. It is in this a paper from 15, and something more about it in a paper from 19. But I have a very recent paper where this is worked out also in the non-smooth situation. And then we have, okay, first, sorry, before I go on to that, I should say if 0 is an eigenvalue here in the smooth case, the eigenfunctions are as smooth as possible. They are in C infinity. It was when the lambda was different from 0 that we had this limitation. Okay, now non-smooth cases. So we have this C tau situation. P is C tau. Sorry, I want to get rid of this. P is C tau and omega is C1 plus tau, where tau is greater than 2a. Then we get this result for the eigenfunctions. Those with lambda different from 0 are in d to the a times c to the minimum of 2a and tau minus a. That's almost as good. When tau is 3a, it's just 2a here. And then there's a minus epsilon. And u naught is in c tau minus a minus epsilon. So it's really just an epsilon weaker than what was true in the C infinity case. And still quite satisfactory. And epsilon is any small positive values and always chosen so that this exponent avoids an integer, because then it's not true for integer. I mean, these are the Hilbert spaces that are defined for non-integer exponents. Okay, and much of this was new even for the fractional Laplacian, and I would say much of the next style is also new. also for the fractional Laplacian. Okay, as a corollary, when we combine this knowledge that the eigenfunctions are rather smooth with regularity theory, we find that the spectrum of the Q Dirichlet realization is the same as the L2 spectrum. I mean, the lambda for which p minus lambda is not bijective is again just those in the L2 spectrum. That holds for all Q between 1 and infinity, and the eigenspaces are the same for all Q. Okay, now one also wants to study the adjoint of the Dirichlet realization. That's an operator in the dual space LQ prime. And it's not quite simple when there's not smoothness, but it can be done and it leads to a satisfactory result. Namely, the adjoint of P dq is the analogous operator for P star in the dual space, P star dq. The difficulty is that when the symbol of P is allowed to be non-smooth, then P star is usually not quite as nice as P. There's some rather substantial error terms when you can calculate the adjoint. And more results here, then you can simply look at the mapping properties of the operator P dq minus lambda, which goes from the domain, which we know is this transmission space, to LQ. And the mapping property is when lambda is outside the L2 spectrum, the mapping is bijective. And when lambda is inside the spectrum, the mapping is a Fredholm operator with kernel in lambda. We already had that kernel, and a co-kernel in prime lambda bar. This is the null space of the adjoint realization minus lambda bar. And you can lift these mapping properties a little bit to HAS plus 2A. S plus 2, this is the case, S equals 0. So you can lift it to small s that go up to the minimum of 2A and 2A minus 1 over Q as well. Remember, I didn't put it in the slides. You can lift them a little. Okay. So that is about the mapping properties and the eigenvalues and the eigenfunctions. And then there's also a question you would naturally ask, namely, what about what about the asymptotic behavior of the eigenvalues? And there's a result there also. And here I just consider the self-adjoint case. In the self-adjoint case, the eigenvalues form a non-decreasing sequence. I mean, they're repeated according to multiplicity that goes to infinity, and one expects a Weil formula to hold, and indeed it does. So the result is this. We take P symmetric, and the symbol is allowed to depend C tau on X only, and the domain is allowed to be Lipschitz, not I mean, all the way down to Lipschitz, and the theorem surely holds for still more general domains, but at least to fix it, yes, let me say it holds for Lipschitz domains. Then this sequence of eigenvalues has the asymptotic behavior one would expect, namely certain constant times j to the power 2a over n. 2a is the order, n is the dimension, plus a little o of j to the power 2a over n. And the coefficient here is defined from the principal symbol by this formula, where you take the principal symbol, integrate it over the unit sphere, take it to the power minus NO2A, integrate it over the unit sphere, integrate it over omega, put a constant in front, and take the power minus 2A over n. That's the standard formula you would get just for P without any boundary conditions. And this is in a very recent paper, and there it's also shown how one can include perturbations. I'm just taking perturbations that give the same Dirichlet domain. And here one can allow a term P prime and a term P double prime, where P prime is a pseudo-differential operator of order less than 2a, minimum of 2a and a plus a half. P double prime can be just a bounded operator in L2, for example, the multiplication by a function, by a bounded function in a potential in L infinity. So those operators will also have the same transmission space domain, and this fact will hold for them also. So that was spectral results for the homogeneous Dirichlet problem. And now I will get to a non-homogeneous Dirichlet problem. That's the last part of the talk. And maybe you will find it a little bit strange, or you will have sort of to twist your brain a little bit to capture what's going on then. So let's get to non-zero boundary values. And here the tradition in this case for the fractional Laplacian, at least for many people, is to say, well, we want a non-homogeneous Dirichlet problem, we get it just by prescribing a value of u in the exterior. So we, instead of having a zero here, we put a function g. And then we call that the non-homogeneous Dirichlet. And some people say, well, they call it the exterior value Dirichlet problem. And it has good sense because you can solve it by extending g to a function on the whole space and subtract that from u, then you get another function u prime, and you get and u prime satisfies the zero condition outside. And the discussion is then what happens when you make the extension and how smooth can you make it and so on. I'm not so interested in that type of non-homogeneous problem. I want a genuine boundary condition, a non-homogeneous boundary condition. And here, as you could see from the results I've already talked about, u is zero on the boundary because it has the factor d to the a, which is zero on the boundary. So you couldn't take it, the usual Dirichlet condition, to have a value on the boundary that doesn't fit in. You can take another value, and here it comes. One can pose this condition on the boundary. One can pose that u divided by d to the power a minus 1 should equal a function phi on the boundary. So gamma naught is the usual notation of the boundary value. Gamma naught of a function v is the value of v on the boundary. So now we consider a non-homogeneous problem with a local boundary condition. We can ask pu to match f in omega, and we ask this object to take a value phi on the boundary, and we ask the support to be still in omega closure. And I will try to motivate it a little. Well, I would first say where does it come from? Well, it was in the first papers I wrote. It was already in Amanda's notes from '66. And at exactly the same time as or 1 week after I put my paper on Archive, there was a paper by Abatangelo, completely independent, also in 15, who actually also considers this condition in a more obscure form. It's not clear from his paper. Well, it's on the ball. He says that his condition identifies with his condition, but he doesn't do it for general domains in that paper. Okay, so I'm not the only one who has thought of it. It comes also from this direction. His approach was from trying to write a Green's formula. I mean, there is a Green's kernel solving the homogeneous Dirichlet problem, and you can play around with that and see what happens if you formulate some integral operators, and then you arrive actually at this condition. And that has good solvability properties also. And now I will motivate it a little more. I will recall that when omega is smooth, if we take the smoothest possible situation for the homogeneous Dirichlet problem, then when f is C infinity up to the boundary, the solutions are in the space d to the a times C infinity. That was one of the results I had, number 4, on an earlier slide, that the solutions form the space d to the a times C infinity. And I will give a name to that space. In general, call it EA. So there's a general name E mu. Script E mu is a space of extensions by 0 of d to the mu times C infinity of omega. So here everything is smooth, and then it gets this fractal. Okay, and what can we say about the functions there? Well, they have expansions at the boundary in powers of the distance that are derived from the Taylor expansions in C infinity and then multiplied by d to the mu. And let's go to local coordinates. Let's replace omega by Rn plus, the half space, where the boundary has the coordinates x prime and the normal direction has the coordinate xn. And so the distance is simply xn. And here, the space EA is characterized by the expansions in the right in Rn plus. The function u is expanded as xn to the a times a Taylor expansion. So it gives the terms function on the boundary times xn to the a, another function times xn to the a plus 1, another function times xn to the a plus 2, and so on. Okay, there's some binomial coefficients that I'm absorbing in V. So here, this is the expansion that holds for functions u in EA when xn is positive. And let me also look at EA minus 1. So I put mu equal to EA minus 1. And then similarly, I have the functions here. Oh, this should have been plus. Then u has the expansion that begins with a function on the boundary times xn to the a minus 1, and then comes a function times xn to the a, and a function times xn to the a plus 1, and so on. And compare these two expansions. What's the difference between them? Well, the only difference lies in this first term. The only difference between expansion 10 and 11 is the presence of this term. And what is V naught here? Well, V naught is what you get by dividing with xn to the a minus 1 and take the boundary. So the difference, well, if we carry that back to the general domain and look at how EA compares to EA minus 1, then an element here is in EA when this term vanishes. And that's the boundary value of u divided by the distance to the a minus 1. So EA minus 1 is EA plus things that have this thing different from 0. And I can formulate a theorem about that. First, let me observe that we can show that R plus P also maps EA minus 1 into C infinity. That's something you have to show for this to make sense. So the problem 9, now I'll just claim it for the fractional Laplacian to have unique solvability. For the fractional Laplacian, the problem I had on the previous, the non-homogeneous problem is Laplacian u should hit a function f in omega. This boundary value should hit a function phi on the boundary, and the support should still be contained in omega bar. And then the statement is, this problem is uniquely solvable with a solution in EA minus 1. And what's the proof? Well, the proof is you look at the problem, you take a function w in EA minus 1 that has this boundary value. You can do that because of the description. You can have any smooth function V naught in front here. And subtract that from u then you get a function v, u minus w, that solves the problem with the boundary value 0. And then we're back at the homogeneous Dirichlet problem, and that's uniquely solvable. And so we get unique solvability of the non-homogeneous problem. That is surprisingly simple, but it's still true. And let me shed more. Let me make another comparison. I'll compare it to the Dirichlet problem for the standard Laplace operator, also on a smooth domain. Standard Laplace should be equal to f in omega. Boundary value should be phi on the boundary. And I know that for f in C infinity and phi in C infinity, there is a unique solution in C infinity. C infinity corresponds to E naught. The extension by 0. If we forget the extension, it's simply the C infinity functions on omega. And then we can consider this was the non-homogeneous Dirichlet problem. And now the homogeneous Dirichlet problem is where you put a 0 here. And this, of course, has a unique solution because the non-homogeneous has it. And the solution of the homogeneous Dirichlet problem has first boundary value equal to 0, and the functions are in E1. So we have the play between E0 and E1 corresponds to what I had for EA-1 and EA in the fractional case. Okay, so that's the nice, easy story in C infinity, in the phi infinity setting. Now let's go to Sobolev spaces and Bessel potential spaces. And of course, it becomes more difficult. We want to discuss solvability results in general Sobolev space, and then what should EA-1 be replaced by? Well, it's replaced by the A-1 transmission space, HQ A-1 of T. And it's defined in local coordinates from this, how it looks in Rn plus. EHQ A-1 of T is the lifting by this order reducing operator of the extension by 0 of HQ bar T minus A plus 1, so minus A-1 in bracket. And this lifting is the operator with this symbol. And it turns out that it works very nicely. Let's see, we first have to define, well, we have to define it on omega, and that is done by local coordinates. These spaces are larger than the HATQ spaces because they contain functions with a singularity d to the A-1 at the boundary. And the solutions are blowing up like d to the A-1. So Abertangelo called them blow-up solutions or large solutions. And that name is sort of instructive, so we kept that name. And here the theorem goes as follows. The problem 9, the non-homogeneous problem, is uniquely solvable, Fredholm solvable in the case 0 is an eigenvalue in the Dirichlet problem, in the homogeneous problem. It's uniquely solvable when f is given in HSQ, phi is given in an appropriate Bezier space of the boundary, and the solution will lie in this A-1 transmission space. And in the non-smooth cases, it holds when S lies between 0 and tau minus 2A-1, and tau and omega is C1 plus tau, and the symbol is C tau in X. So there is an existence and uniqueness theorem, or Fredholm solvability theorem, when 0 is an eigenvalue, in this situation with solutions in this space. Okay, now let me pass to a spectral parameter. What happens if we take a spectral parameter into the business? Well, you wouldn't be surprised. It can be done too. And again, now here we have to be careful. We replace p by p minus lambda, so we want to act with this multiplication by lambda. And therefore we need the spaces that we are working on to be in LQ. because the right-hand side will be at least in LQ at worst. Okay, what the A-1 transmission spaces are not always contained in LQ. We take the case where S is 0, the right-hand side is in LQ. And then the solution space here, when is that in LQ? Well, if you look at it carefully, you see that it happens when Q is sufficiently small. It's still greater than 1, but less than 1 minus A inverse. In that case, the solution space is contained in LQ, and we can do a study of P minus lambda. And here we note that Q can be taken to equal to 2. We are in an L2 case when A is greater than 1/2. And then in this situation, we can include the spectral parameter and find the following theorem. So here's the equation. A plus PU minus lambda U should match an F in omega. Non-homogeneous boundary condition. This boundary value has to match a function phi on the boundary and the support contained in omega closure. And the result is when lambda is not in the L2 spectrum, it's uniquely solvable. And when lambda is in the spectrum, it's Fredholm solvable. And we can also tell what the kernel is and the co-kernel is. So nice solvability result still holds. Okay, then what more can be said? Well, I'm sort of nearing the end of my talk, but I want to make some comments on another contribution to this question. I mean, this problem was also studied by Chan, Gomez Castro, and Vasquez in a paper that was published in JFA 21, just for P equal to the fractional Laplacian, and based on the knowledge of the Green's kernel for that. And sort of like Abertangelo, I mean, there's a joint work with Abertangelo and Vasquez also, and one of these people. And what they do is they compare the L2 setting with a formulation in weighted L1 spaces. So they go out to L1, which is more than we do. We stay with LQ spaces for Q greater than 1. And they also have a weight. So they go out into larger spaces. And they make special comments on the problem where F is 0. So I repeat it here with F equals 0. PU minus lambda U should be 0 now and satisfy the boundary, the non-homogeneous condition, and U should have support in omega bar. And this problem, they regard this as an eigenvalue problem. I mean, okay, the first line does look like an eigenvalue problem, but there's this funny requirement about the boundary value. And then they call the solutions large eigenfunctions. They're called large because they blow up at the boundary. They have this blow up. I mean, they behave like d to the n-1 at the boundary. And they find it very mysterious and very wonderful that they can find large eigenfunctions solving this problem. They show the existence of solutions when lambda is outside the L2 spectrum, and then they discuss what happens when lambda converges to an element, to an eigenvalue. And it's sort of a colorful paper full of enthusiasm, but it also seems to me be mystifying. I mean, they make it overly mysterious because, I mean, I'm not surprised that this boundary value enters because it fits very naturally into the general theory. So I'll end with this remark. And then I have one page more, which is just references. So I will go back. I mean, you can look at them if you get the copy of the slides. So I'll end here. Thank you.
So the group, thank you very much for this very wonderful talk. So we are open for questions. Now, I will allow the participants to unmute by yourself. If someone has questions, just unmute your microphone and go ahead. Any question or comments?
Maybe I can ask a question if it's okay. Yes, thank you. Sorry, I just saw someone.
Can I see you?
So it is still okay? I go ahead. Yeah. Yes. Sorry, I wanted to ask by comparison and analogy with the theory of layered potentials for the Laplace operator, that we have a kind of duality with the adjoint operator. So the Dirichlet problem becomes adjoint to the Neumann problem on a bounded domain for these layer potentials. And likewise, the Neumann problem has its dual adjoint Dirichlet. Is there such counterpart in this context of fractional Laplacians?
Well, it's a very nice question. I would like to have a reference to what you're talking about, but it gives me the possibility to say that you can also impose a Neumann condition here. I mean, you can put gamma 1, I mean, the normal derivative of this function equal to a given function on the boundary. That makes good sense too, also for the fractional Laplacian. But I didn't know the result that you're referring to, so I'd be glad to look into it.
So I think this is probably, I mean, in Folland's PDE book, or people like Marius Mitria or Jill Pfeiffer, I mean, these kind of people work on the. Yeah. And the point is that somehow when you move from the C2 boundary to Lipschitz boundary, the compactness of the kernel operator is kind of lost. So there are some added complications there. So I mean, it would be nice to see what the counterparts in this fractional context.
Yeah. I would say the fractional context. Well, it hasn't. I mean, they're not. The fine results are still lacking in the case of a Lipschitz boundary. There are studies of a Lipschitz boundary by numerical people, both Gerd and Acosta and what they call. I didn't have them on the list, but well, they're on the first list on the first page. But they work in Lipschitz spaces, and they don't get up to this distance, the effect of the distance to the boundary. They stay within low order Sobolev spaces, so they don't exhibit what you're talking about.
Okay.
So I mean, certainly, I mean, it would be interesting to see if one can push the theory further for Lipschitz spaces, but it's sort of open still.
Okay, thank you.
Thank you very much. So Tobias Castro.
Yeah.
Okay. Tobias, have you a question? Yes, please.
Oh, thank you. Well, what a wonderful talk. I just congratulate from Colombia, Tobias.
Oh, okay.
I just have a question. I would like to know what is the main reason to localize the spectrum of the fractional Laplace operator. What is important?
What is the reason? You mean the reason to go to a domain omega instead of space?
To know the region where the spectrum is a subset. Why this is important?
Well, I mean, there certainly there are applications in probability where you, well, by Brownian motion is a language I don't know, but I mean, they speak of processes, Levy processes, that have different conditions at the boundary. And one of the processes they're interested in is this Dirichlet problem that I started out by defining. I think it enters in the financial theory too. I mean, if it's just one-dimensional, it would be the full line is okay, corresponds to Rn. But if you have the half line, something happens at 0, and you need a condition there. You need a way to interpret the operators. That's as close as I can get to motivation. But there are certainly many motivations in probability for these. for the interest of these problems.
Thank you.
Thank you, Tobias. So, any other question? I have, maybe I have a question about myself. I am just curious about the properties of eigenfunctions. So you show this asymptotic behavior.
Yeah.
But my question is if are known in this context LPLQ estimates for eigenfunctions, like the ones by Gormanden and so on, in terms of
You mean two-term asymptotics? I mean better.
yeah.
Okay, I would say that with the methods I'm using, I could make slightly better asymptotics. I could get a remainder instead of little o, I could get a big O of something slightly better, but not as the step one lower dimension. That has not, well, I would say, by the way, I could say Ivry, Victor Ivry, he claims he can show, but he doesn't give the details. I mean, he posted that he could give a two-term asymptotics for the fractional Laplacian on a smooth set. But the proof, if you look at his argumentation, you just say that it goes in the same way as something way down in the middle of a very large book he has written. And so I wouldn't be able to track it, what the proof is. So it's considered as an announcement, actually.
Okay, I see. Thank you very much. So any other question? Okay, if not, just...
yeah, Gihon has a question. Please,
okay.
Gihon, go ahead.
Gihon, please, go ahead.
Yeah.
Okay, my name is Gihan Lee, and I'm a postdoc working in Michael's research group. And first of all, thank you very much for the very nice and inspiring talk. And I'm sorry, but could you go back to theorem 4 in?
Yes. 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 Yeah. Is that?
Yes. So for me, it seems like this formula 8 this has the form of the Utsitsky's the non-commutative residue of the given the operator. So
there's a connection, certainly. I mean, you're quite right. It looks very much like it. I worked with these things about 15, 20 years ago. So I must say I'm not quite fresh on them right now. I mean, there are links between the coefficients that appear. Also the heat, I mean, in the heat trace expansion, the first term has this coefficient and the second term has another coefficient and so on.
So I suspect that there would be some relation.
I'm sure there is, yes.
And
yes.
The spectral, the values like the singular values of the given operator or the Biot's law of the domain.
Yeah, I think that I think there are relations, and I could, well, maybe in some days if I went back into my own papers and leaf through them, find the connection. But you're right. I mean, there are connections between these things. No, I would say. Now I begin to remember. You take the. Yeah, I wish I could write, but I can't really. I don't have the tool for that. If you do the heat trace expansion, you take exponential of minus p t.
Yes.
And expand that in t. You take the trace of exponential of minus p t and you expand that in t.
Sure.
You have a number of terms, and the first term has this coefficient, and the nth term has a coefficient that's related to the residue.
Yes.
Residue is what you get by the is I think proportional to the to the nth term in this for John case.
I see.
It's a formula that can also be reduced to just depending on P naught. That's right. And it looks very similar. There's an integral over the sphere and an integral over omega. So I think now that I remember this about the heat kernel, I think it's not the same formula, but it's another formula that involves P naught that goes into the residue. I mean, it's another term. It's sort of you're talking about the index theory and
Yeah.
things that enter into that. I mean, there's the rough formula that uses a lot of symbols and a lot of derivatives, and it can be boiled down to something that only depends on P naught, I think. Yeah, that's as close as I can come on the spot.
I see. Okay. Thank you very much for your answer.
Thank you, Juho, for your very nice question.
Yeah.
Okay, any other question? Or comment?
Curiosity. Professor, can you go to Formula 4,
Yes.
please?
Yeah.
Yeah, in that result, you didn't say anything about the A. This is the optimal one, because in the other ones you were saying, like, you cannot go up, you cannot go
Oh,
down.
yeah, but this formula is for the general solution. When I mean, the formula where I couldn't go up, that was for the eigenfunction.
Ah, okay, I see.
Here, the general solution is in dA, C infinity. Let me go to the other statement so make more precise what I'm talking about here. I'm saying that the eigenfunction for lambda different from 0 lies in this space and not better, or that space, not better. But if 0 is an eigenvalue, we are in the best possible space.
Oh, yeah.
So if you have 0, if you have PU equals 0, that's the null solutions. They are in the best possible space. But the eigenfunctions for a lambda different from 0, they're only in these spaces, not in the better space.
Yeah, you're right. Thank you.
Yeah, and something I have not included at all in the talk is that this lambda parameter, it also has an importance when you look at the evolution equations. I mean, heat equations with the fractional Laplacian. Then here the resolvent is in some sense equivalent to the heat operator, and then this information gives you some limitations on how good the solutions are to the heat equation, the associated heat equation. And that's in my paper 19 from 19.
Thank you, Professor.
Thank you. Any other question or comment?
Sorry, I have a question, please.
Okay, please go ahead.
Thank you. Thank you, Professor, for this nice talk. I have just a question on the first equation.
Yeah, I can.
The fractional Laplace.
I hope I can't see you. I have to find
Yes.
you.
Okay, I'm sorry.
Who?
And the first equation.
So now, shall I go back to some?
Yeah.
Yeah.
Equation number 1.
Yeah. The very first here.
Yeah. My question now is it possible to solve this kind of equation with just boundary conditions?
No, that's the whole point. Well, with just standard boundary conditions, no. If you
Or it depends on the definition we give to the fractional operator.
No, but take this operator. That's the one we want the information on. Put it in here. Then to say that it's not a well-posed problem to say that the boundary value should be 0, because it will be 0. I mean, if we have u being 0 outside, then it's found that u has a factor d to the a, distance to the power a. So when you go to the limit at the boundary, you get u equals 0 for free. I mean, and you cannot prescribe the boundary value of u to be 0. That will not make sense. It will not give a good problem.
Yeah. Wow.
But we have to, but we take the weighted boundary value, that works. The one way to u divided by d to the a minus 1. That works to give a uniquely solvable problem. But the standard boundary values don't work here.
Yeah, thank you.
That's what I can say.
Okay. Thank you very much. So any other question? Maybe. Okay, maybe we can stop. So Professor Gerd, thank you very much for your very nice talk. And you always are welcome to our Ghent geometric analysis seminar. So Santiago, you have information for the next seminar, maybe?
Yeah, may I just say,
Yes.
Thank you
Yes.
very much to have the patience to listen to all this that I was telling, and thank you for some very good questions. It was a pleasure to talk here. Thank you.
Thank you. Yes.
Thank you very much, Professor. Yes, just changing the page. Yes, next week we will have a mini course, but by one of our postdocs here in the center. I think it will be about Lorentzian geometry. So please get posted. I will send a reminder at the end of this week. So I hope you will enjoy the topic. So that's what I have to say. Thank you very much, everyone, for attending today. And I guess see you next Monday.